All right, what's good, everybody? Welcome back to another day in the learning journey. It's been a little bit since I've done this. I guess I've just been busy, or I don't know, a little bit of busyness, a little bit of laziness. But yeah, past doesn't matter. All that matters is today, what we're doing right now, and the future. So yeah, as always, got my curiosity with me, and of course, got my coffee with me as well. A little bit later in the day, so we're gonna be chilling off of some decaf today. Yeah, without further ado, let's get right into it. Gonna start with our language focus of the day. So let me get right into it. We're gonna review some hiragana, I believe this was, and this is gonna be ju. We've got bya, ryu. All right. Mu is right there. Chu is right there. We have byo, ip, pyo, ze, po, do slash zu. Ru is right there. I believe this to be. I'll say rat. Okay, it's wa. Fair enough. We have bu. Oh god, I messed up. All right, ra. Mia is gonna be right. Not right. Or mute is right there. What am I even saying right now? Ga. We have gu or gyu. To is right there. Definitely got to up the consistency. I can definitely tell I'm slightly washed at the moment. Ooh. All right, we're going to tat Bargachi machine. Not very happy with the 89%, but it's okay. This is going to be Mafuin, I believe. And let's consult good old Google Translate. Mafin. Okay. That has been noted. Pretty cool badge right there. We're going to focus review hiragana. We're going to bump up the quiz size to 60. And yeah, we have zo, which is right there. Sho is going to be right there. Su. Ku. Ne is right there. Ji. A. Nya. We have no. Et. Ryu is right there. Gi. She is right there. We have Ket. Set is going to be this guy right there. We've got Tet. New. Hyo. Real. So is going to be this guy right there. Who is going to be right there. Wo is right there. He. Get is going to be this guy right there. We have Hya right there. Met. Sha. Ah. This is going to be roll, I believe. Nice. We have root, which is going to be, I believe that to be that one. Nice. You right there. We've got hot. All right. A little over halfway done. Got to keep the ball rolling. That's going to be neat. Kyo. Zu right there. Wo. Then. Bet is this guy right there. Da. Wo. This is going to be, let's see, I want to say rat. Okay, nice. Easy money. We've got Bio or Pio. Oh, is going to be that guy. We have got Yu, Ki, Su, Yo, Biu, Ya, This is gonna be met. Oh, it's new. Damn, we were going so good up until that point. Oh well, though, mistakes happen. Just gotta learn from them. That's what really matters. So we've got nyo, ya, do, cho, i. We've got za, kyu, ta, mi, and last but not least, de. Nice. Okay, we only missed one. Would have liked to get the 100%, but you know, just wasn't in the cards, I suppose. Can't really trip about it. Gotta just keep moving, like I said a little earlier. This is going to be new. All right, 98%. Oh, we can evolve our little homie. Let's see. Ah, he's got a cat now. Very cool. All right, let's tap the gacha machine. Got hot dog, which is going to be. Is this Hatsudogu? I probably completely butchered that, but let's see. Hatodogu.
Hotdog.
Hatodogu. Okay. It's interesting that these two together make hato, given like that's like I believe tsu. Maybe, I don't know. Maybe I'm just don't know what I'm talking about. All right, let's focus review, which honestly that's probably likely the case. All right, 60 more. Let's get right into it. I believe this to be meh. Very cool. Deep. Not. Mo. Hyo. Yu. Ru. Ooh. Ro. Ooh, okay. Second guess myself. Shouldn't have done that. All right, noted. We got Cho. Nya right there. Gi. U. Su. Mu. Po. Or Bo. Bia is going to be right there. And P. We've got Re. Wa. Okay. All right. Q. Net. Sho. We've got Nu. Ta. Ja. Su. Jo is right there. Ku. U/Zu. Zo. Ya. Chu. Te. Ya. Yo. De. Ki. Yo. Yu is going to be this guy right there. We've got So. Ju. O. A. Ke. Shi. U. Yo. Ro right there. Oh my god. I'm not on it today. It's okay. All that matters is I'm here and I'm trying. Yeah. I'm trying to learn from my mistakes. That's the most important. Got Ryo is going to be right there. He E/G is going to be this guy. Cha is right there. Got Ma right there. Cool. Do is going to be this guy. Ra. Nyo. Tet. Was a little bit unsure. Tried to bail out, but we got it right anyways. Zep. And then last but not least, we missed 2. Oh, we missed 3 actually. Shoof. Sheesh. Root. Rope. And then Wa. Okay. Wa, Re, and Ne. I mean, I'm pretty confident about Ne, but like Wa and Re kind of trip me up. I'm not gonna lie. 95%. What do we get? What do we get? Inoko. Let's see. Kinoko is mushroom.
きのこ
Kinoko. Very cool. Alrighty. Moving on to katakana. Let's settings, focus review. We're going to hit that 55 number because it says we still have 55 more to review. And I'm going to take a little victory swig of coffee for a little bit. All right. This is cheap. Gyo is right there. Ju is right there. O. Chu. Ket. Ma. I. Get. Tsu or Shu. This is gonna be Mo. Crazy. As soon as I take a swig of this decaf coffee, I start yawning. All right. Hia. We have Wo. U. Ria. This is going to be New. Pia. Za. Pi. This is going to be beat. Sha is going to be this one right there. Ki. O. Be. Nya. This is going to be Ra. Okay. It was between one of the two. Got it wrong. It's okay. Kya is going to be right there. Ku. Sa. O. Zo is going to be this guy. Nice. Bo. D/G. To. Ba. Like a sheep. We have Te. Ka. I. A. Pa. Pyo. You right there. Ra. Gyu. Ga. So. Cho. Go. I messed up. Shit. Okay. U. N is gonna be that one. Nice. Okay. A little bit unsure there. Would like to be more sure moving forward. U is gonna be this guy. Neat. And then last but not least, Nu, because it looks like the number 7. Miss 2, not bad. Go is going to be that. And then I believe we said that was Ra. Okay, cool. 96%, like to be better. What is this? Is that edamame? Oh, edamame. I was just looking at that, but then I like put it in my brain, this stuff down here. And yeah, sure enough, it is edamame. Very cool. All right. Study, get these last 28 terms that we haven't gone through yet. Kyo. Hyo is right there. Pyu. Bio. Da. Q is going to be right there. Rio is right there. Ya. Jo. Okay. Cha is going to be right there. Sho is right there. Mia is right there. Zu. Ji. Mio is right there. Bu. Mu. Ryu. This is gonna be Ja. This is Bu. Do. Nyo. Z. U is right there. Du slash Zu is this guy. Bia. Shi. And then Pa. Alright, easy money. 100%. Let's go. Alright, this is Ushi. Let's see. Survey says Ushi is cow. Bet. Bet, 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 bet. Take a little swig of coffee as well. Alright. 16 words went up in mastery. Cool deal. Love to hear it. I think we move on to words for basic Japanese. I believe there's 29 if memory serves me right. Try and hit each one evenly. Sushi, obviously the dish was vinegared rice. Nichiyobi, Sunday. I wish for those ones for Saturday and Sunday it would give me both of those options. I feel like that would really help me kind of differentiate the two. We have Yumai is famous. Yep, nice.
有名
Yume. Okay. Spare time is going to be not Takai. It's gotta be Yasui. Oh shit.
暇
Ima, okay. Kyo. Alright. Nihonjin, a Japanese person. Shinsetsu is what we're looking for there. Yo. Or you. Let's see. Anata. Alright,
あな
nice.
た
We have Utsukashi, or Mutsukashi is difficult. Isha is doctor. Ansamu is right there. We have Gakusai, it's going to be student. We have Heya, like the Outcast song, that's going to be room. We have Takai. Amerikajin, right there. Tomorrow is going to be Ashita. Right there. Saturday is going to be Doyobi. Kaishain is going to be company employee. Cheap, inexpensive is going to be Yasui. Atsui is going to be, I believe, hot. Nice. We have Kore, which is... It's this. Nice, cool.
これ
Kore. We have Oishi, it's going to be good tasting. Busy, occupied, hectic, relentless. That is going to be... let's see here. Isogashi?
忙しい
Okay, cool. I was looking at Muzugashi and I was like, well, no, that's not it because that's difficult. But yeah. We have Karuma right there. Shiken is going to be exam. And Pitsu is what we're looking for right there. Here, this place. Koko. Cool. We have Genki, that's going to be lively, full of spirit. And Pen is going to be pen. All right, we missed one, which is it Isogashi? No, okay, Hima. Okay, I fell into literally the same trap, so Hima. All right, 97%, like to be better. Let's see. This is Onkochiu. Let's see. I highly doubt that's what it actually is. I think I completely just butchered that, so let's find out. Oh, handkerchief. Hankachifu. Okay, I just messed up that one at the end. Hankochifu. We're going to study basics. So obviously, des is at the end. Wa. And then let's see, sushi is delicious. So sushi is the subject. So sushi would come first, no? That? Okay, cool. Now let's hear it pronounced.
寿司は美味しいです。
Sushi wa oishi desu. Alright. Let's see, we have des, wa, this is what, kore? He is Japanese, so nihon, or no. It would be this. Yeah. And then that. Okay, cool.
彼は日本人です。
Kare wa nihonjin desu. Alright. And then last but not least, we already have des, so we're just going to put wa right there. And he is not kind, so we're going to do... I believe that goes right there. And Shinsetsu, and then Janai. Okay, cool, nice.
彼は親切じゃないです。
Kare wa nihon, kare wa shinsetsu ni janai desu.
彼は親切じゃないです。
Kare wa shinsetsu janai desu. Okay, cool. Easy money. We're not going to join Renshu Pro right now, unfortunately. We're going to see how we fare. I'm using other resources probably. This is going to be Oyatsu. Yeah. Bada bing, bada boom. Oyatsu. Snack.
おやつ。
Oyatsu. Okay. Alright. So that's pretty much everything we can do without getting pro. So we're gonna migrate on over to YouTube. I'm gonna make a duplicate tab. And let's see here. Japanese sentence. Further review some Japanese sentence structure. Let's watch. What do we want to watch? What if we just take out the sentence structure and just do Japanese sentence? How does this differ? Our results. I guess we can watch this one. Why not?
In the college setting, this is your first impression, your first time. You want to put your best foot forward. I'm Lauren Taylor.
Grammarly's cool, but actually knowing how and why grammar goes together might be even more beneficial, which Grammarly could probably be a tool as that, but using crutches of any kind in life are really not ideal, like unless you need to, you know.
Sentence structure, which is how to build a sentence in Japanese, and also I will give you some examples. At the end, I will do quizzes, so be prepared for that. Hi
Gonna
everyone,
hit us with a quiz, shit.
Sensei desu. So let's get started. Hajimeyo.
Hajimayo.
So, the sentence structure in Japanese is different from English, as you guys all know. For example, in English, I ate sushi. I, subject, ate, verb, and sushi is noun. But in Japanese, always the verb comes at the end. Verb is ate, well, to eat. Let's do with to eat. So for example, I eat sushi. 私は寿司を食べる。
Wait, whoa.
寿司。私は
Tashi
寿
wa
司を食べる。This is
Tashi
how
wa-
you build the Japanese sentence. 寿司を食べる。This is how you build the Japanese sentence.
Watashi wa
Many of my students,
sushi wo
this is how you build the Japanese sentence. Many of I eat sushi. 私は寿司を食べる。
Watashi wa sushi wo taberu.
私は
Okay.
寿司を食べる。
Watashi wa sushi wo taberu.
Sentence. Many of my students are having tough time to build a long sentence. Like Mochi Sensei, how to do this? So I'm gonna tell you the easiest tip to remember it. Okay. First, subject, and then when, where, with whom, and what you did, which means the verb. Subject. いつ、どこで、誰と、何をした。This is the basic sentence structure. If you notice, it's much more easier to build a sentence. But one thing to tell you is that this might be changed. This order might be changed. Depends on the sentence. Like, I went to the park with Tom yesterday. In English too, this sentence structure might be changed, right? Like, yesterday, Tom and I went to the park. So these two sentences are completely same meaning in Japanese too. So this order might be changed, but the basic is this. Then let's do more example. So first, I went to the cinema. This sentence, there's no detail about when, itsu, and also with whom, 誰と, there's no detail in this sentence. So you can just ignore it, skip this. The information we need is subject, I, where, to the cinema, what you did, I went. So in Japanese, it's gonna be 私は映画館に
Watashi wa Eigaka ni ikimashita. Watashi wa geiki fuck.
It's gonna be 私は
Watashi wa
映画館に
eigaka ni
来ました。
ikimashita.
Cinema is
Watashi wa geiki na mani.
And 映画, just 映画. This means movie. So I
What'd she say?
行きました。
Ikimashita.
Cinema is 映画館 and
映画館
just 映画. This means movie.
Eiga.
So I went to the
Okay.
cinema. 私
Getting a
は
lot of knowledge thrown at us right now.
行きました。Let's do the next one. I drank a beer yesterday. I drank a beer yesterday. There's information about subject, I, and when, yesterday. And there's no information about where and with whom, so just skip it. And at the end, the verb comes, drunk. So it's gonna be 私は昨日
Watashi wa kinu biru
飲みました。
飲みました。
飲みました is what you did yesterday, right? Let's do a little bit more examples. I will study Japanese with sensei today. I will study Japanese with sensei today. Sensei is a teacher. So in this sentence, there's a lot of information. I, subject, when, today, with whom, with sensei. And what are you gonna do? We'll study Japanese. So in Japanese, this will be 私は今日
私は今日先生と
日本語を勉強します。私は is subject. When? 今
I
日
gotta get used to
today.
like
With whom?
see I feel like I can when I look at these like I can it takes me a little bit to like look at the symbol and be that's Nihon and then do you know like that, but yeah, in the time that I'm like thinking about it or in the time it takes me to think about it, I guess the sentence is already passed when you're talking about it,
先生と
or like
What
when
are you gonna
someone's
do?
talking about it.
日本語を勉強します。Okay, then before quiz, let's do one more
I'm about to
example.
freaking bomb this
I
quiz.
will read a book at the library tomorrow. I will read a book at the library tomorrow. So in this sentence, again, I, subject, when, tomorrow, where, at the library, with whom. There was no information about that, so just skip. And then at the end, we'll read a book is what you're gonna do. So in Japanese, 私は明日図書館で本を読みます。If you know this sentence structure, it's easy, right?
When, where, with whom, what you
And
did.
let's do the quizzes. Quiz number 1. How to say today. I will go to my friend's house. Today. I will
All right, we have your friend's house would be the or no, I guess.
go to my friend's house.
I feel so stupid.
The answer is 私は今
私は今
日
日
友達の家に
友達の
私は今日友達の家に行きます。Quiz number 2. I watch a movie every day. I watch a movie every day. Hi. The answer is 私は毎日映画を見ます。私は
I almost wish she'd separate the masu from this so that I can better focus on what the word is, but I guess that's just me complaining about not knowing really what I'm talking about. So watashi wa mainichi
映画私は毎日
私は毎日映画を
私は
見ます
毎日映画を見ます。Okay, the last quiz. I will do a little hard one.
Oh.
Today,
Is that the other ones
I
weren't hard
ate
enough? Sheesh.
pasta at the restaurant with Tom. Today, I ate
Yeah, there's no shot I'm getting this
at
one.
the restaurant with Tom.
Might only even be able to pronounce maybe half of it if I'm lucky.
The answer is 私は今日
私は今日
レストランで
レストランで
パス
ト
タを
マト
食べました。Did you
Okay.
get them all correct?
Oh yeah,
So
100%.
again, summary is the sentence structure in Japanese is subject いつどこで誰と何をする。I hope this information will help you and thank you for watching. See you guys in the next video. Bye.
Alright, very cool. Let's like it up, help the algorithm of course. Yeah, let's get into the learning structure because I don't want to fry my brain too much
Learn
before I get into the
Japanese
more
with great
technical stuff.
Japanese TV shows.
いた。
どうだった？
どう？
皆さんこんにちは。ここは松山城の近くです。お城は行ったので、これから道後温泉に行きます。
Does dogo mean like dojo?
Google マップで見たら、
Is that the same word?
歩い
Not
て
the same word, but
30
relatively the same meaning, or am I just completely off? Who knows?
あの路面電車に乗れなかったので、
Pretty cool train.
歩くことにしました。そんなに遠そうに思えなかったからです。でも結構遠くて疲れてしまいました。あまりに疲れたのでバスに乗ることにしました。ここがバス停です。
Oga?
バスが来ました。バスに乗れて本当に
There's some of my subtitles in English. Or are they both in English? I guess is my.
4分で次のバス停に着きました。
Okay. There we go.
あ、すいません。どうもありがとうございました。すいません。
Hinton driving.
少し楽ができました。
Kashi. Little.
今から行くのは道後温泉です。
There's Dogo Onsen. The
道
hot
後
spring.
温泉は日本で一番古い温泉とも言われています。
That's
レ
a pretty
トロ
cool
な見
bin
た目のバスですね。
bus. Was Mitame.
古そうな建物が見えてきました。あれは道後温泉本館です。この建物は千と千尋の神隠しに出てくる
Oh,
お
that
風
building's
呂
cool
屋
as
さ
hell.
んのモデルになった場所の一つです。
Ah.
いくつかモデルになった
Knew
場
I
所がある
recognized
そう
it. Spirited
で
Away is
す。
one of the goats.
お風呂には今回は入りません。でも中の見学を予約していました。予約はしてますがチケットを買います。
すいません、立神殿の予約してるんですけど。
この後困ったことが起きます。何が起きたのか聞いてみてください。
あ、いやだ、すごい間違えた。私5月25に予約してた。ごめんなさい。そうなんですね。ではそちらキャンセルして本日にされますか？いいですか？はい、何名様でいらっしゃいますか？1人です。1名様ですね。はい。はい、すいません、よかった。何日のご予約ですか？5月25の4時になってました。4時ですね。はい。確認しますのでお待ちください。はい、申し訳ありません。
この日は5月
この日
19
は
日でした。
で、
日付を間違えて予約していました。
ちょっとお名前とかご予約のお名前とか確認をさせていただきたいので、担当者が今参りますので、はい、じゃあちょっとこの辺に。はい、すいません。
担当者というのはその係の人のことです。
あ、はい、そうです。お名前伺っていいですか？はい。 これが予約
1028号で。はい、じゃあこれキャンセルで。
はい、キャンセルで。
今日見れる。わかりました。もうチケット買いました。
あ、買ってないです。
これから。はい。わかりました。
Man, she said, let me speak to the manager. That's crazy.
もう一度並ぶ必要がありました。さっきより人が増えてました。やっと私の番になりました。
はい、有志年のチケット、はい、お願いします。
では中に入りましょう。靴を脱いで靴箱に入れます。
あ、すいません、有心電の。はい、駐車券ございます。あ、ないです。見学お2階になりますので、廊下の突き当たり左の階段から上にお進みください。ありがとうございます。
突き当たりというのは、それ以
Skiatari?
上まっすぐ
Dead
に
end.
行けない場所です。この階段を上がります。
はい、チケット拝見します。はい、これです。1名様、はい、どうぞこちらです。はい、チケット番号1名様です。こちらにチケット出してください。
じゃあ今、どうしたらですね、今海外の方が行かれたので、はい、その方出られてからになります。大丈夫ですか？
わかりました。はい。あ、15分とか待ってればいいんですか？
はいはい。はい、じゃあこちらの方にちょっとピンナップをくださいませね。
はい。ありがとうございます。
こちらの方に
Sensory overload. Holy cow.
は、ここに座ってという意味です。
これがですね、
I'm freaking out right now. We need a plan. Make your choices.
It's interesting. We got recommended a chick flick right there.
はい。わかりました。
温泉の方が予習をしとってくださいと言いました。しとってくださいは方言でしておいてくださいという意味です。予習というのは授業の前に自分で勉強することです。つまり見学の前に勉強しておいてください。
Pretty confused about what's happening on that screen. I'm not gonna lie. Should study before the tour.
ここは何でしょうか？
ここは何でしょうか？
下まで階段
I
が
gotta look more at the
続いてい
symbols
ます
unless it like these English words right here. Hita.
この下には皇室の方についてきた女性のためのお風呂があるんだそうです。今は閉まっているそうです。見学の時間になりました。
じゃあ改めまして皆さんこんにちは。
Might actually turn off my subtitles.
道後線の方にお越しいただきまして誠にありがとうございます。それでは今からですね、全国で
There's just too much text going on.
全国唯一でございますけれども、皇室専用の温泉施設でございます有心殿のご見学を今からしていただきます。
皇室というのは
皇
天皇
室
家のことです。皇室専用というのは皇室の方のためだけのものという意味です。
はい、どうぞ皆さんお入りください。
失礼します。
ここは休憩するお部屋だそうです。その横の階段を降ります。ここがお風呂です。このお風呂は70年以上使われていないそうです。お風呂にはお風呂用の 絹の着物を着て入ったそうです。
Oh, I heard kimono. I know those are pretty expensive.
こちらは着替えるスペースです。少し高いところで天皇家の方が着替えるんだそうです。さて、その隣、これがなんだかわかりますか？トイレです。漆のトイレだそうです。
Oh, is that a toilet?
見学が終わりました。面白かったです。では、これから駅の方に向かいます。道後温泉本館の前は商店街です。商店街はお店がたくさん集まっている通りです。通りの上に屋根があるところが多いです。
Oh, Totoro's right there.
ジブリのお店がありました。見てみましょう。顔なしです。コインを入れ
It's
そうですね。
like a Studio Ghibli fan shop.
これは友人の花屋さんにあったものです。この辺は文房具が売っています。こだまのノートです。ジジがかわいいですね。これはコースターですね。
Alright, that might do it for this portion. So, for the language portion, we're going to leave a like, show some support. Yeah, I'm going to go run to the bathroom real quick, and then we'll get into some math. Yeah, some math, learning derivatives and stuff. So, yeah, be right back. Alright, and I'm back. So let's get into this math portion. Without further ado, we're going to resume our derivative learning. Yeah. 3 out of 4 questions to level up. Okay. It's been a little bit since we've done this, so probably gonna...
In the last video, we tried to figure out the slope of a point or the
not
slope
remember
of a
stuff,
curve
but it's
at
okay.
a certain point. And the way we did it, we said, okay, well, let's find the slope between that point and then another point that's not too far away from that point. And we got the slope of the secant line. And it looked looks all fancy, but this is just the y value of the point that's not too far away, and this is just the y value of your point of the point in question. So this is just your change in y, and then you divide that by your change in x. So in the example we did, h was the difference between our two x values. This distance was h, and that gave us the point, the slope of that line. We said, hey, what if we take the limit as this point right here gets closer and closer to this point? If this point essentially almost becomes this point, then our slope is going to be the slope of our tangent line, and we define that as the derivative of our function. We said that's equal to f prime of x. So let's see if we can apply this in this video to maybe make things a little bit more concrete in your head. So let me do one.
Yeah, that'd
First,
be
I'll do a
nice.
particular case where I want to find the slope at exactly some point. So let's say, let me draw my axes again. Let's draw some axes right there. And let's say I have the curve. Let's say I have the curve. This is the curve. Y is equal to x squared. So this is my y-axis. This is my x-axis. And I want to know the slope at the point x is equal to 3. And when I say the slope, you can imagine a tangent line here. Do it in a light yellow. You can imagine a tangent line that goes just like that. And it would just barely graze the curve at that point. But what is the slope of that tangent line? What is the slope of that tangent line, which is the same as the slope of the curve right at that point? So to do it, I'm going to actually do this exact technique that we did before, and then we'll generalize it so you don't have to do it every time for a particular number. So let's take some other point here. Let's take some other point up out here. Let's call this 3 plus delta x. I'm changing the notation because in some books you'll see an h, some books you'll see a delta x. Doesn't hurt to be exposed to both of them. So this is 3 plus delta x. So first of all, what is this point right here? What is this point right here? This is a curve y is equal to x squared. So f of x is 3 squared. This is the point 9. This is the point 3, 9 right here. Let me draw that out. Well, I'll draw it out in a second. And what is this point right here? So if we were to go all the way up here, what is that point? Well, here our x is now
3 plus delta x squared.
Delta x. It's the same thing as this one right here. Is x naught plus h. I could call this 3 plus h just as easily. So it's 3 plus delta x up there. So what's the y value going to be? Well, whatever x value is, it's on the curve, is going to be that squared. So it's going to be, this is going to be the point 3 plus delta x, 3 plus delta x squared. So let's figure out the slope of this secant line. Let's figure out the slope of this secant line. And let me zoom in a little bit because that might help. So if I zoom in on just this part of the curve, it might look like that. And then I have one point here, and then I have the other point is up here. So let me see if I can draw that. That's the secant line. Secant line, just like that. This was the point over here. This point is the point 3, 9. And then this point up here is the point 3 plus delta x. So it's just some larger number than 3.
3 plus delta x
that
squared.
number squared. So it's going to be 3 plus delta x squared. What is that? That's going to be 9. I'm just foiling this out, or you do the distributive property twice. If you a plus b squared is a squared plus 2ab plus b squared. So it's going to be 9 plus 2 times the product of these things. So plus 6 delta x, and then plus delta x squared, plus delta x squared. That's the coordinate of the second line. This looks complicated, but I just took this x value and I squared it because it's on the line y is equal to x squared. So the slope of this line, the slope of the secant line is going to be the change in y divided by the change in x. So the change in y is just going to be this guy's y value, which is 9 plus 6 delta x plus delta x squared. That's this guy's y value minus this guy's y value.
9 minus 9.
So minus 9. Minus 9. That's your change in y. And you want to divide that by your change in x. By your change in x. Well, what is your change in x? This is actually going to be pretty convenient. This larger x value, we started with this point on the top, so we have to start with this point on the bottom. So it's going to be 3 plus delta x. 3 plus delta x. And then what's this x value? Well, it's minus 3. Minus 3. That's his x value. So what does this simplify to? The numerator, this 9 and that 9 cancel out. We get a 9
delta
minus
x
9.
plus 6.
And in the denominator, what happens? This 3 and minus 3 cancel out. So the change in x actually end up becoming this delta x, which makes sense because this delta x is essentially how much more this guy is than that guy. So that should be the change in x, delta x. So the slope of my secant line, so my slope has simplified to 6 times my change in x plus my change in x squared, all of that over my change in x. All of that over my change in x. Now we can simplify this even more. Let's divide the numerator and the denominator by our change in x. And I will switch colors just to ease the monotony. So my slope of my tangent of
This makes sense to me right now, but sure, once I get a problem, once I'm faced with a problem or something, it's all going to escape me.
By delta x plus 6 plus delta x. So that is the slope of the secant line. So slope is equal to 6 plus delta x. That's this one right here. That's this reddish line that I've drawn right there. So if this number right here, if the delta x was 1, so if this was the point, if these were the points 3 and 4, then my slope would be 6 plus 1, because I'm picking a point 4 where the delta x here would have to be 1. So the slope would be 7. So we have a general formula for no matter what my delta x is, I can find the slope between 3 and 3 plus delta x, between those 2 points. Now, we wanted to find the slope at exactly that point right there. So let's see what happens when delta x gets smaller and smaller. This is what delta x is right now.
I'll say you use a limit now.
Delta x got a little bit smaller, then it would start, the secant line would look like that. It got even smaller, the secant line would look like that. It gets even smaller, then we're getting pretty close to the slope of the tangent line. The tangent line is this thing right here that I want to find the slope of. So let's find the limit as our delta x approaches 0. So the limit as delta x approaches 0 of our slope of the secant line of 6 plus delta x is equal to what? This is pretty straightforward. You can just set this equal to 0 and this is equal to 6. So the slope of our tangent line, at the point x is equal to 3, right there, is equal to 6. And another way we could write this, if we wrote that f of x is equal to x squared, we now know that the derivative, or the slope of the tangent line of this function at the point 3, I just only evaluated it at the point 3 right there, that is equal to 6. I haven't yet come up with a general formula for the slope of this line at any point, and I'm going to do that in the next video.
Okay, that was straightforward enough, I suppose. Let me move on to here.
In the last video, we found the slope at a particular point of the curve y is equal to x squared. But let's see if we can generalize this and come up with a formula that finds us the slope at any point of the curve y is equal to x squared. So let me redraw my function here. It never hurts to have a nice drawing. So that is my y-axis. That is my x-axis right there. My x-axis. Let me draw my curve. It looks something like that. You've seen that multiple times. This is y is equal to x squared. So let's be very general right now. Remember, if we want to find, let me just write the definition of our derivative. So if we have some point right here, let's call that x. So we want to be very general. We want to find the slope at the point x. We want to find a function where you give me an x, and I'll tell you the slope at that point, and we're going to call that f prime of x. That's going to be the derivative of f of x. But all it does is, look, when you f of x, it's a function that you give it an x, and it tells you the value of that. And we draw the curve here. With f of x, you give that same x, but it's not going to tell you the value of the curve. It's not going to say, oh, this is your f of x. It's going to give you the value of the slope of the curve at that point. So f of x, if you put it into that function, it should tell you, oh, the slope at that point is equal to, if you put 3 there, you'll say, oh, the slope there is equal to 6. We saw that in the last example. So that's what we want to do. And we saw in the last, I think it was 2 videos ago, that we defined f prime of x. We defined f prime of x to be equal to just the, well, I'll write it this way. It's the slope of the secant line between x and some point that's a little bit further away from x. So the slope of the secant line is change in y. So it's the it's the y value of the point that's a little bit further away from x. So f of x plus h minus the y value at x, right? Because this is right here. This is f of x. So minus f of x. All of that over the change in x. So if this is x plus h here, the change in x is x plus h minus x, or this distance right here is just h. The change in x is going to be equal to h. So that's your slope of the secant line between any 2 points like that. And we said, hey, we could find the slope of the tangent line if we just take the limit of this as h approaches 0. Limit as h approaches 0, and then we'll be finding the slope of the tangent line. Now let's apply this idea to a particular function, or f of x is equal to x squared, or y is equal to x squared. So here we could have the point, we could consider this to be the point x squared. So f of x is just equal to x squared. And then this would be the point, let me do it in a more vibrant color. This is the point x plus h, that's this point right here, it's a little bit further down. And then x plus h squared, And in the last video, we did this for particular x. We did it for 3, but now I want a general formula. You give me any x, and I won't have to do what I did in the last video for any particular number. I'll have a general function. You give me 7, I'll tell you what the slope is at 7. You give me -3, I'll tell you what the slope is at -3. You give me 100,000, I'll tell you what the slope is at 100,000. So let's apply it here. So we want to find the change in y over the change in x. The change in y over the change in x. So first of all, the change in y. The change in y is this guy's y value, which is x plus h squared. X plus h squared. That's this guy's y value right here. That's this right here. That's x plus h squared. I just took x plus h, evaluated I squared it, and that's its point on the curve, so it's x plus h squared. So that's there right there. And then what's this value? F of x right here is equal to, I know it's getting messy, this is equal to x squared. If you take your x, you evaluate the function at that point, you're going to get x squared. So it's equal to minus x squared. This is your change in y. That's this distance right there, change in y. And just to relate it to our definition
So
of
it's
a
kind of
derivative,
just rewriting what
this
he
blue
wrote
thing right
earlier,
here is
essentially,
equivalent
just
to
in
this
more
thing right here. We just
broad
evaluated our
sense
function.
and not
Our
specified
function
at
is f of
a
x
given
is
at a
equal to x
specific
squared.
x
We just
value.
evaluated when x is equal to x plus h. So if you have to square it, if I put an a there, it would be a squared. If I put an apple there, it would be apple squared. If I put an x plus h in there, it's going to be x plus h squared. So this is that thing, and then this thing right here is just the function evaluated at the point in question, right there. So this is our change in y, and let's divide that by our change in x. Our change in x, if this is x plus h and this is just x, our change in x is just going to be h. So that's where we get that term from. So this is just a slope between these 2 points. This is just a slope between those 2 points. But of course, we want to find the
And then you
limit as
limit
this
it.
point gets closer and closer to this point, as this point gets closer and closer to that point. So this becomes a tangent line. So we're going to take the limit as h approaches 0. And this is our f prime of x. And this is the exact same definition of this. Instead of being general and saying for any function, we know what the function was. It was f of x is equal to x squared. So we actually applied it. Instead of f of x, we wrote x squared. Instead of f of x plus h, we wrote x plus h squared. So let's see if we can evaluate this limit. So this is going to be equal to the limit. Let me write a little neater than that. The limit as h approaches 0. To square this out, I'll do it in the same color. That's x squared plus 2xh plus h squared, and then we have this minus x squared over here, minus x squared. I just multiplied this guy out over here, and then all of that is divided by h. Now let's see if we can simplify this a little bit. Well, you immediately see you have an x squared and you have a minus x squared, so those cancel out. And then we could divide the numerator and the denominator by h. So this simplifies too, so we get f prime of x is equal to, if we divide the numerator and denominator by h, we get 2x plus h. Oh, sorry, I forgot my limit. It equals the limit, very important, limit as h approaches 0 of divide everything by h, and you get 2x plus h squared divided by h is h. And if you remember the last video, when we did it with a particular x, when we said x is equal to 3, we got 6 plus delta x here, or 6 plus h here. So it's very similar. So if you take the limit as h approaches 0 here, that's just going to disappear. So this is just going to be equal to 2x. So we just figured out that if f of x, this is a big result, this is exciting, that if f of x is equal to x squared, f prime of x is equal to 2x. That's what we just figured out. And I want to make sure you understand how to interpret this. F of x, if you give me a value, it's going to tell
Oh,
you
I
the
see.
value of the function at that point. F prime of x is going to tell you the slope at that point. Let me draw that, because this is a key realization. And you might, it's kind of maybe initially unintuitive to think of a function that gives us the slope at any point of another function. So it looks like this. It looks like, let me draw a little neater than that. That's still not that neat. That's satisfactory. Let me just draw it in the positive coordinate, although, well, I'll just draw the whole thing. The curve looks like something like that. Now, this is the curve of f of x. This is the curve of f of x is equal to x squared, just like that. So if you, I don't know, you give me a point. You give me the point 7. You apply, you put it in here, you square it, and it is mapped to the number 49. So you get the number 49 right there. This is number 749. You're used to dealing with functions right there. But what is f prime of 7? F prime of 7, you say 2 times 7 is equal to 14. What is this 14 number here? What is this thing?
Slope of the
Well, this is
tangent
the
line.
slope of the tangent line at x is equal to 7. So if I were to take that point and draw a tangent line, a point that just grazes our curve, if I were to just draw a tangent line, that wasn't tangent enough for me. So that's my tangent line right there. I think you get the idea. The slope of this guy, you do your change in y over your change in x, is going to be equal to 14. The slope of the curve at y is equal to 7 is a pretty steep curve. If you wanted to find the slope, let's say that this is y, let's say it's x is equal to 2. I said y at x is equal to 7, the slope is 14. At x is equal to 2, what is the slope? Well, you figure out f prime
4.
of 2, which is equal to 2 times 2, which is equal to 4. So the slope here is 4. The slope is 4. You could say m is equal to 4, m for slope. What is f prime of 0? F prime, we know that f of 0 is 0, right? 0 squared is 0. But what is f prime of 0? Well, 2 times 0 is 0. That's also equal to 0. But what does that mean? What's the interpretation? It means the slope of the tangent line is 0. So 0 sloped line looks like this. Looks just like a horizontal line. And that looks about right, that a horizontal line would be tangent to the curve at y equals 0. Let's try another one. Let's try the point in minus minus 1. So let's say we're right there. X is equal to minus 1. So f of minus 1, you just square it because we're dealing with x squared, so it's equal to 1. That's that point right there. But what is f prime of minus 1? F prime of minus 1 is 2 times minus 1. 2 times minus is minus 2. What does that mean? It means that the slope of the tangent line at x is equal to 1 to this curve, to the function, is minus 2. So if I were to draw the tangent line here, the tangent line looks like that. And look, it is a downward sloping line. It makes sense. The slope here is equal to minus 2.
All right, pretty cool. Let's move on. We can calculate the slope of a tangent line using the definition of the derivative of a function f at x equals c, provided that limits exist. So we're substituting c for x here, so we get the limit as h approaches 0 of f of c plus h minus f of c over h. Once we've got the slope, we can find the equation of the line. This article walks through 3 examples. What is an expression of f of x equals x squared at x equals 3? So you do h approaches 0. So 3, you're going to substitute 3 in for x. Yeah. Let's see. Find the equation of the tangent line at to the graph of f of x equals x squared at x equals 3. Okay, so f of x equals x squared, x equals 3. So you do 3 plus h squared because you're trying. Let me think through this. I think it would be 3 plus h squared. So it'd probably be one of these two minus h squared, which would be minus 0 squared. We're trying to find as h approaches 0. Right? Then you get a divide by 0 error, so that couldn't be it. Be that? Okay, cool. Kind of use this to come up with it. X plus h squared minus x squared over h. 3 plus h squared minus 3 squared over h, which f prime of 3, where we said f prime of, we said that f prime of x for an, whatchamacallit, for an exponential thing is just 2x, so that'd be 6. Okay. Step 3, what point should we use for the equation of the line? F prime of 3 gives us the slope of the tangent line. To find the complete equation, we need a point the line goes through. Usually that point will be where the tangent line touches the graph of f. Okay. What point should we use for the equation of the line? I would say c comma f of c. What do we do? Let's see. So it'd be 3, wouldn't be 3 comma 6, I don't think. Might need to explain. f of 3 equals 3. Oh, okay, so you just plug it back in. That makes sense. Okay. 3 comma 9. Therefore, the point is 3 comma 9. Complete the equation of the tangent line to the graph of f of x equals x squared at x equals 3. Complete the equation. So y, complete the equation of the tangent line. So we said the slope of the tangent line is 6. So you do y equals 6x plus 6x plus 9. No. Okay, you do y2 minus y. Wait. We're looking for the equation of the line whose slope is 6, and that goes through the point 3 comma 9. To do that, we can use, okay, so we have the, so we just need to find another. Now we can isolate the y. So you, okay, so from here, let me try and imagine this and visualize it. 6x minus 3 equals y minus 9. You'd probably want to factor that out before moving on. So you'd get 6x minus 18 equals y minus 9. So 6x plus 9 equals y. Okay. Okay, and we're done using the definition of the derivative. We were able to find the equation of the line tangent to the graph of f of x equals x squared at x equals 3. Okay, so f of x equals x squared, that's the graph, and then x equals 3, we're looking for that. Okay. Find the equation of the line tangent to the graph of g of x at x equals, or at g of x equals x cubed at x equals -1. So we would do limit of -1 plus h cubed minus -1 cubed over h. I think that sounds right. Okay, next. We would do so I believe you'd factor this. Let me pull up Paint and at least try. Probably gonna get it wrong. Doesn't really matter. As long as I'm trying, all that really matters. Paint down. Alright. Hopefully my penmanship isn't too bad today. So we would do the equation of the tangent line. We're simplifying this. So -1 plus h, -1 plus h, so you do h squared, h squared plus 1. I think. I don't know. Probably wrong, like I said. And then times h minus 1. So in turn, I believe you'd get h cubed minus h squared plus h minus 1, and then -1 cubed is going to be -1, so times -1 over h. You're going to get negative h cubed, oh god, cubed minus h squared, oh wait, plus h squared minus h plus 1. All of that over h. I'm going to put this in and it's going to be wrong, but it doesn't matter. At least I tried. It's most of the battle. Bring it up on my second screen. We got negative h cubed minus h squared minus h plus 1 for h. Okay. So let's see what they did. Let me bring this down. I would say factored it. So negative 1 cubed plus 3 negative 1 squared. Where are we getting plus 3 negative 1 squared from? None of this isn't really making sense to me, if I'm being honest. Okay. We got 3 somehow. Next question, at what point does the tangent line... Okay, wait, so what do we get? Oh, we said that's 3, right? Okay. Alright, so the slope of the tangent line as h approaches 0 is 3. At what point does the tangent... Okay, so we'd plug... Would we plug negative 1? It would be negative 1, negative 1. Okay. And then finally, y equals 3x plus, what do we do up here? So we have 1, negative 1. So let me go back to here. Copy up. Okay. So we have, I'm just going to try and replicate this. 6 was our slope of the tangent line there. So we're going to do 3 equals y minus b. Y plus 1 over x 1 multiplied by x plus 1, get 3 1. Then we subtract 1. Then we simplify 3x plus equals y subtract 1. Get y. I don't think that's right. No, it's not. Explain. What do we do? Therefore, oh. Oh, wait. So it'd be 3x plus 3 minus 1. So plus 3x plus 2. No? Any equivalent form is acceptable. That's fucking cap. The equation of the line. Okay, so that would be -1. The equation of the line. Okay. Y equals 3x plus 2. Okay, I guess. Let's do this one without all the steps. What is the equation of the tangent line? Sounds like other people are getting crazy confused about this as well. Let me see what they say. We plug x equals -5. And f of x equals x squared. Plus 3 in the definition for the derivative. Yeah, I'm just go back to this, try again. I'm just not very good at this right now. Which derivative is described by the following expression? As x approaches pi, sine pi minus, or sine x minus 0 over x minus pi. So it'd be f prime of pi, because that's what we're trying to find as the limit approaches pi, where x equals sine over x. No. Since the limit is for x approaches pi, we know that this is the derivative at x equals pi. Okay, got that. Is also indicated by x minus pi, okay. Since the numerator is a quotient, sine 0 is equivalent to sine of x minus sine of pi. F of x equals sine of x. Wait, why? It's indicated by the denominator in the quotient expression x minus pi. Since the numerator in the quotient expression sine of x minus sine of pi, so sine of pi is equal to 0. No? I'm just getting insanely confused here. F prime of 4 for f of x equals root x. F, so as x approaches 4, root x minus 4 over x minus 4. Pretty sure you would include both of them. Maybe not. Dude, this is just so fucking... I'm getting so confused right now. Ah, man. Go derivatives. Ooh, I misspelled that. Hmm. What do I want to do? Watch this and try and see if we can understand him in a different way. See, like, I kind of understood that.
Every discipline of
like,
science has its
I
very
don't know,
own
man.
special language, the way it communicates the ideas that it investigates. For example,
I was way
biology
better at
finds
this in
order in the world
college.
by giving every living thing a name in Latin. Chemistry has a system of prefixes, suffixes, and numerals to tell you in a word or two the exact composition of an atom or a compound. Physics has to communicate its ideas differently. The language of physics is mathematics. Because if you're trying to describe how the world works, you really have to know how things relate to each other in a mathematical way. For example, we've been talking a lot about position, velocity, and acceleration, and how they're all
Make sure
connected.
my,
Velocity is a measure of your change in position,
go.
and acceleration is a measure of your change in velocity. They're connected. One quality will describe how the other is changing. And the way we describe change in mathematics is through calculus. Calculus explains how and why things change using derivatives, which help you to determine how an equation is changing, as well as with integrals, which you can use to calculate the area under a curve. Derivatives and integrals themselves are closely connected, but let's start with derivatives. You probably won't be able to go straight from this lesson to your calculus final, but hopefully in about 10 minutes, you will be able to understand some of the maths that scientists have been using to think about physics for the last 400 years or so. And you'll also have a new way to fight speeding tickets, you know, just in case.
It's quite the animation there.
Last time we talked about that unfortunate incident where you got a speeding ticket. Your speedometer was broken, but because we knew your acceleration, we were able to calculate how fast you were going when the cops pulled you over. So now, let's talk about what happens next. Say the police drive off. You're ready to get back on the road, so you hit the gas and zoom forward, moving faster and faster. But in this scenario, we don't know your acceleration. We only know how much your position is changing over time. In this instance, your position happens to be equal to the amount of time you've been driving squared. So we'd write that as the equation x equals t squared. 20 seconds in, you pass a detector with a sign that tells you your speed. You keep driving, foot still on the gas, before you realise what number you saw on the sign. And oh no! You just got a speeding ticket in the last episode for doing 126 kilometres an hour in a 100 kilometre an hour zone. And now the
Speed
detector
racer
says you're
over
going
here.
even faster. Now you want to know if the number on the detector is accurate. In other words, you want to find your velocity at the exact moment you passed it. That velocity is just a measure of your change in position. It's derivative. So to find your velocity, we'll need to find the derivative of your position. And in order to determine that, we first need to talk about limits. Not speed limits, I mean the derivatives kind. I'll explain. Limits are based on the idea that if you have an equation on a graph, you can often predict what it's going to look like at one point just by knowing what it looks like at the surrounding points. For example, let's say you have a graph of x equals t squared from our speeding scenario above. And you want to find out how your position is changing at the exact moment that time is equal to 0. That is what we call a limit as t approaches 0. So you take a look around at what's happening around t equals 0. At t equals 1, x is 1. At t equals 0.5, x is 0.25. And at t equals 0.1, x is 0.01. You can probably tell that as we get closer and closer to t equals 0, your value of x is getting closer to 0 too. That's what mathematicians mean when they talk about a limit. Limits are useful because they can help predict what happens as you make intervals smaller. An interval is just a range on a graph. It's the space between 2 points on the horizontal axis. So the first thing we can try is calculating your average velocity over the interval from 15
That would be
to
your
20
secant line, no?
seconds. To do that, we use an equation that we talked about last time, your average velocity, which is equal to the change in your position divided by the change in time. That turns out to be 35 meters per second. Problem is, it's just an average. It's not exactly how fast you were going after 20 seconds of acceleration when you passed the detector. Because of limits, we know that you could get a little closer to the right number by calculating your average over smaller and smaller intervals. Then you'd see that the number seems to be getting closer and closer to 40 meters per second, which means you're going to need to slow way down if you don't want to get your second speeding ticket of the day. But that's the idea of derivatives. You can use infinitely tiny intervals to figure out exactly how an equation is changing at any moment. You can even come up with an equation to describe the change. That's exactly what velocity is, an equation that describes change in position. And acceleration describes change in velocity. So we call velocity the derivative of position and acceleration the derivative of velocity. Now, when it comes to how you can express a derivative in writing, mathematicians have come up with shortcuts, like what's known as the power rule. As the name suggests, it's used for equations with variables raised to powers or exponents, as long as the exponent is a number. For example, x equals t squared would work with the power rule.
The derivative would be
t is raised to the
2t.
power of 2. The power rule says that for these kinds of equations, to calculate the derivative,
I think
all
Khan
you need is
Academy
one
are just
weird
going
trick.
way
Take the
too in
number of
depth
that
and confusing the
exponent,
shit
in
out of
this
me.
case 2, and stick it in front of the variable. Then you subtract 1 from the exponent. And that's your derivative. So the derivative of x equals t squared is just 2t, which means that no matter how many seconds you've got your foot on the gas, your velocity will be 2t. So double the number of seconds. After 5 seconds, you were going a modest 10 meters per second, but after 20 seconds, you were going a full 40 meters per second, which is not good. We'd write that like...
Then following this exponent rule, the derivative of x cubed would be 2x squared.
this, where dx
That's
over
right.
dt is just a way of saying that we're taking the derivative of the part of the equation that involves t. Or, as a mathematician would put it, we're taking the derivative of x with respect to t. You'll also sometimes see this written in a different way. If f of t is equal to t squared, then f prime of t is equal to 2t. Now let's try to find a couple more derivatives using the power rule. X equals 7t to the power 6 is another power style equation.
X equals
It has a
42t
variable t
to the
raised to the
fifth.
power 6 with a number in front of it, 7. The first thing we do is take the exponent and stick it in front of the variable. But there's already a number in front of t, 7, so we end up multiplying them. 7 times 6 is 42. Then we subtract 1 from the power that t is raised to, so we end up with 42t to the power 5. Same goes for equations where the exponents are fractions or decimals. So the derivative of t to the power half is half t to the negative 1/2. It works for negative exponents too. The derivative of t to the power minus 2 is just negative 2t to the negative third. Now, there are a few more equations whose derivatives you should understand. Trigonometry, which we use to calculate the angles and sides of triangles, is going to come up a lot in physics because we'll be using right-angled triangles all the time. So it's a good idea to know how to find the derivatives of sine x and cosine x. Sine tells you that if you have a right-angled triangle and x is the angle in that triangle, then sine x will be the length of the side opposite that angle divided by the hypotenuse. Cosine does the same thing, just with the side next to the angle, divided by the hypotenuse. So their graphs will tell you what those ratios will be depending on the angle. We can actually try to guess the derivative of sine x just by looking at its graph. You can see that the curve has turning points every so often at x equals minus 90 degrees, x equals 90 degrees, and so on, repeating every 180 degrees. Meaning at those points, the equations aren't changing at all. So the derivative at these turning points is also going to be exactly 0. Let's pull up another graph where we'll plot the derivative and put little dots where we'll know it'll be 0. Now, what's happening between those turning points? Well, from minus 270 to minus 90 degrees, sine x is decreasing. In other words, its change and therefore its derivative must be negative. Then, from minus 90 to 90 degrees, sine x is increasing, so it will have a positive derivative, and so on. There are actually a lot more clues in this graph to help us find the derivative, but we already know enough to make a decent guess. If we smoothly connect the dots on the graph of our derivative, keeping in mind where the curve should be positive and where it should be negative, hey, this derivative is looking a whole lot like the graph of cosine x. That's because it is. The derivative of sine is just cosine, and that's going to come up a lot. And so will these, which you can work out on your own by repeating what we just did with the graphs of sine x and cosine x. Another important derivative that comes up a lot is a very special case, and that's e to the x. The derivative of ex is just ex. Yep, and that's it, no matter what. In fact, that's one way to define e, which is kind of like pi, in the sense that it's a simple letter representing a very specific, irrational number, about 2.718, but with more digits after the decimal point that go on forever. It has all sorts of uses in calculus, but it also shows up when you're studying things like finance and probability. Armed with all these ways to find derivatives, you could pretty much take any equation of your position and calculate its derivative, and therefore your velocity. In the same way, you could take the derivative of your velocity and find your acceleration. But there's a whole other part of calculus that we haven't even talked about yet. Integrals, which will let you do this backwards. With integrals, you can use your acceleration to find your velocity and your velocity to find your position. But we'll save that for next time. Today you learned about limits and that derivatives use them to describe how an equation is changing. We also talked about a few different kinds of derivatives, powers, constants, trigonometry, and e to the power x. Crash Course Physics is produced in association with PBS.
Alright, that was pretty informative. Yeah, really helped me simplify stuff. Especially from the deep dive that was the Khan Academy course. Sorry, I got caught up reading one of those, or reading one of the comments. Yeah, I think we're gonna change gears. No pun intended, depending on what we choose to watch, and watch I guess a lot less technical video, different kind of technical. I don't know. I feel like my brain's a little fried right now. Let's watch Transistors.
If I were to ask you what the most important advancement humankind has ever made, what would you say? Many would make the case for fire. Our species was in an evolutionary rut until we harnessed its power. It gave us the warmth to survive harsh winters. Its light extended our day, its destructive powers gave us a weapon against predators, and it allowed us to cook our food, which allowed our brains to grow. Our discovery of fire transformed not only our technologies, but our culture and our way of life. But I would argue that we are currently living in a time of equal or even greater change. We are living in a time of incredible growth, one that has already started to transform the way we live our lives. The age of information. With 40% of the world's population currently connected to the internet, the human race is more intertwined than ever before. But what led to this amazing tool? What single invention gave rise to our smartphone-equipped generation? The transistor. The transistor is information itself. Even this video is just a series of ones and zeros beaming across the planet to be interpreted by the processors in your computers. Without the transistor, I wouldn't have access to the wealth of information online to do my research, I wouldn't be able to use my animation software to make these videos, and I certainly wouldn't be able to share it here for the world to see. The transistor is so simple, but it is the foundation of all our modern computers. To understand its impact, we need to understand the history and science behind it. Before the transistor existed, we used vacuum tubes, which are these bulky evacuated glass bulbs. The triode vacuum tube consisted of 3 parts, the cathode, grid, and anode. A current is passed through the cathode and it begins to heat up, causing it to release electrons. As gases have been removed from the tube, the electrons have very little resistance to their movement, and they are attracted to the positively charged anode. This completes the circuit, and a current flows. But we can manipulate this flow of electrons in many useful ways with the grid. For example, we can use it as a switch. If we place a light bulb here, it will only light up when there's a positive voltage across the grid. If we apply a negative voltage, the negative charge will repel electrons trying to pass through. This is the foundation of binary coding, which is the ones and zeros that gave birth to the age of information. Here 1 is a positive voltage and 0 is a negative. 1 turns the light on, 0 turns it off. The world's first general purpose electronic computer, the ENIAC used 18,000 vacuum tubes to perform calculations. Designed by John Mauchly and J. Presper Eckert, it was completed in 1945. It was purpose-built to calculate trajectories for artillery during World War II. A calculation that would take a human a day to calculate took ENIAC 30 minutes. But this thing weighed 30 tons and took up an entire room. It was incredibly power hungry, as the vacuum tube cathodes needed to be heated to work, which also meant that the vacuum tubes burnt out regularly and needed to be replaced. All this to perform a function that your phone basically does with Angry Birds. Today, its computing power could be contained on a silicon chip no larger than a grain of sand, and that's thanks to the transistor. A modern phone has around 2 billion transistors, which perform the exact same job as the vacuum tube, but on the nanoscale. Let's look at how it works. Many of you will recognize the transistor as one of these, but this is a through-hole transistor that you can buy from hobby electronics stores for your DIY projects. The transistors in your CPU are microscopic and are manufactured with incredible precision with machines on thin wafers of silicon crystal that are sliced off silicon ingots like this. So what makes silicon so special that an entire section of the San Francisco Bay Area has been nicknamed after the material? Silicon is a semiconductor, which means its conducting properties can be tailored by introducing impurities to the crystal structure. Silicon has 4 electrons in its valence shell. This is the outermost orbit for electrons, and it determines many of the chemical properties of the atom. Atoms want 8 electrons in that shell, as this makes them very stable. So silicon readily forms covalent bonds with 4 neighbouring silicon atoms to gain those extra electrons. Now, if we introduce those impurities to this pure silicon crystal, we can change how it conducts a current. If we add phosphorus, which has 5 electrons in its valence shell, the extra electron is left free to roam the crystal structure. This extra electron makes the n-type negatively charged, which is where the name comes from. The p-type is positively charged because it is doped with boron, which has 3 electrons in its valence shell. This structure wants to gain its final electron, and will steal electrons from its neighbouring atoms. This creates a mobile positive charge called a hole. The conductivity of the material has thus been increased as we've increased the number of mobile charges. When we arrange n-type and p-type semiconductors like this and attach terminals to each, we create the world's most prevalent transistor, the NPN transistor. The transistor works due to the interaction of those free electrons and holes at the n-type and p-type junction. Free electrons in the n-type will migrate over to fill those holes in the p-type. This creates a boundary layer called the depletion layer, which prevents more electrons passing through due to the negative charges repelling each other. But when a positive voltage is applied to the base, it negates the depletion layer and allows current to flow through, completing the circuit. As you can see, this is very similar to the function of the vacuum tube. So how exactly does this allow computers to perform all these complex functions that we see today? Let's look at a very basic example. Let's add 2 numbers together. First, we need to learn how numbers are represented in binary. That's the 1s and 0s that are used to store data. This is the number 15, which is the largest number you can represent with 4 bits. The first bit represents 1, the next 2, then 4, and finally 8. Added up, that equals 15. This pattern continues, with each successive bit representing double the previous, so we can add an additional bit if we want to count up to 31. Let's add 5 and 6 together. To do this, we want a circuit that will hold a 1 in this position when either are 1, and carry the 1 forward when both are 1. As you can see, this will give us the number 11. The simplest circuit that can do this is a half adder, which contains 2 types of logic gates. These are devices that can modify the binary code. They are built using transistors. The first is the XOR logic gate, which gives a 1 only when one of the inputs is 1. If both are 0 or 1, it gives a 0. The second logic gate is an AND gate, which gives a 0 for everything except when both inputs are 1. If we wire these logic gates like this, we create a half adder, which gives 2 outputs, our sum and our carry. This allows us to add our binary number 1 bit at a time. A more complicated circuit is needed to perform the calculation in one step. Modern computers can perform millions of these calculations per second, and they're still getting faster. The co-founder of Intel, Gordon E. Moore, noticed a trend in 1965 that the density of transistors on integrated circuits doubles every 2 years. That trend has held until very recently, but it is starting to slow down. One of the reasons for this is the less well known of Moore's predictions, Moore's second law, or Rock's law, which states that the cost of manufacturing these devices will double every 4 years. Intel made an announcement last year that the rate of advancement was slowing for these reasons. It's getting more and more difficult for chip manufacturers to shrink their product while maintaining profit. Another problem that transistors are facing is quantum tunneling. As these transistors get smaller, so do the barriers between different sections. The barriers between each section of the transistor are getting so thin that electrons can pass right through them. With no definitive successor to the silicon transistor lined up, this incredible period of growth over the last 50 years could plateau in the near future. Some want to harness quantum mechanics to perform calculations faster than any transistor ever could. Others want to decentralize computing power and create the so-called Internet of Things. Intel have said themselves that they plan to shift their focus from increases in speed to decreases in power consumption. One thing is for sure, the computer industry will have to redefine itself in the near future. Thanks for watching.
The shovel. It was groundbreaking invention. Yeah. I mean, he's not wrong in a very literal sense. What do we want to do? I feel like my brain's kind of fried right now. I would say we can go into some C++, but I think I still need to set up like my IDE and my environment and everything. I can't even English right now. So yeah, I think that's gonna do it for today. Thanks for tuning in. You know, get out there and learn. Even if you don't initially understand shit, like most of the things today, I didn't really understand. But you know, exposure therapy, a way to understanding. Yeah. Anyways, have a good one. Peace out.